Okay, hi everybody. This is recording this lecture in I guess that's the 5th, March 6th, in lieu of our live session um, last Friday. And I apologize in advance for my voice. I caught something on my trip here. I think it's a cold or something like that. So in case my voice goes or doesn't sound particularly even worse than usual. So anyway, what I decided to do today was to actually go back and review Gauss's law one more time for you guys. I covered this at the tail end of our last lecture or the second half of our last lecture, but I don't know if it's for whatever reason. I think it could have been better and probably left some of you guys confused. And it is a slightly confusing concept. So I'm going to go over Gauss's law again. Um, Again, trying to explain it in a slightly different way and hitting mostly the highlights. So I'm going to go over Gauss's law again. And so I guess the first thing I wanted to say about Gauss's law is if you, for a second you forget about the equations and so on, I think it's actually fairly easy to visualize what Gauss's law means. So let's start at sort of a simple concept of just a charge. And let's try to draw the lines of force coming out of this unit charge. So I'm going to choose to draw 8 lines coming out of this. As we've talked in the past, the choice is yours, theoretically speaking, about how many lines you say are used for a particular number of coulombs. So this lines of force or that we're drawing is a visual tool. So the total number is really dependent on what you yourself choose to um, to use. But there are some constraints here. So one of them is the directions of these lines of force. For example, we said this is a point charge, so the lines of force are going to come radially out of this thing. Okay, so that's the direction is pretty well set. And then the second thing is that the force coming out of this point charge has to be symmetric radially. That means like if I chose to, I can't draw this like this because as you can imagine, if I rotated it, then it wouldn't be quite the same. It's asymmetric. There looks like there's more force here than it is here. So again, you have to draw it in a symmetric situation like this. You have to draw the lines of force symmetrically. Okay, so now let's say, so we have this. So without, again, visually, if we can draw just going through again a visual thought process here. If I draw, let me extend these lines a little bit further out. So it's a little bit more obvious. I'm just going to extend them out longer. Let's say if I draw a spherical shape here. So remember, this is a sphere that I'm drawing around this thing. Okay, and let's say I draw also another shape. Let's call this sphere shape, let's call it S. Oops. And then let's say I draw another shape, but this one is like a funky shape, like that. Okay, really funky. And this is another shape, but another shape. And let's call this S prime. Now this is a funky shape, but it still completely encloses the charge. And of course, the sphere also completely encloses the charge. Okay, so visually, just drawing these two shapes, again, I'm sorry about that, I didn't draw this very well. It should be a sphere centered around this charge, but hopefully you get the idea. So visually, you can see that, again, don't think too much about it. Just looking at this picture, you can see that the total number of lines that are going to cross the sphere, there's a total, I drew 8 lines, so 8 lines are going to cross the sphere. The total number of lines crossing the sphere has to be the same as the total number of lines crossing this funky shape, because they're both completely enclosing this charge, so they're going to both completely capture all the lines drawn there. So what we can say is that the lines crossing S is our sphere that I drew, sphere, is equal to the lines crossing S prime. And this S prime is, I don't know, I call it funky shape, but any other shape that completely encloses the charge. Again, this is just visually, you can see that from this drawing and what we described, okay? Okay. Okay, so let's think about the definition of, let me give you guys a definition of line density. Okay, line density, again, hopefully this is all reviews from our discussions earlier. So the line density is defined as the number of lines per area, and this is a perpendicular area. Okay, so what does that mean? So number of lines, so let's say if I look at just this region here, if this is my area, the line density is, there's 2 lines going through this particular area, okay? And the reason why it's this entire area is because I have a sphere, and because these lines of force are radial, the area, the perpendicular area is guaranteed that whatever area draw on the sphere is perpendicular. The area vector is perpendicular to the direction of the the lines of force. For example, if I look at, let's see, this point here on this funky shape, okay, if I go down here, I didn't draw it very well, but like, use your imagination here, you can see that this is not going to be this is a perpendicular area. So this small area, I call it dA, and it's not going to be in, it's the line of force is not perpendicular to the area. So if you want to look at this, I would have to put a dot product, right, to make sure it's pointing in the direction I want. Well, for the sake of discussion right now, let's think of the sphere. Okay, so the line density in terms of S. Okay, so the area perpendicular is guaranteed. This area of sphere, again, on a sphere, is guaranteed to be perpendicular to radial lines coming out. So I can basically say this is proportional to, we have, as we had agreed, the number of lines is proportional to the charge, right? We said, you guys, in this case, I drew 8. We said you could draw something else. We also said you could draw 1 over epsilon naught per Coulomb. So the number of lines is proportional to the charge, okay? And the area of a sphere is equal to 4 pi r squared. So the area is proportional to r squared. I'm not saying equal to, I'm just saying proportional. So the number of lines drawn is going to be proportional to the total charge at the center. And the area of whatever I've drawn here is proportional to 1 over r squared. If I draw this further out, it's going to be a bigger area. Okay. Okay, so separately, we know that from our equation for the electric field. So if you guys just remember, I'll write that. So this is the definition of E field is Q 4 pi epsilon naught 1 over r squared. Okay, so we can say that the electric field is also proportional. Notice it's the magnitude of it is proportional to the Q and also inversely proportional to r squared. Okay, so we can also say the electric field is proportional to Q over r squared. So this is just the strength of E field. I don't have the, there's obviously an electric field vector, but so this is not, does not include direction. What I've drawn here, otherwise I would put a vector there. Okay, so given these two things, the fact that the line density is proportional to Q over r squared, and the electric field is proportional to Q over r squared, we can say, as we already know this, that the line density is, we know it's proportional to E, but let's say it's equal to E with a constant. Okay, so this is some constant. So again, we're saying the line density is proportional to Q over r squared, excuse me, and the electric field is proportional to Q over squared. This is just proportional. But there's some other constants here and there, and we can dump all the constants into a single constant C. So this is some constant. And it depends on what number of lines that you chose to draw. Okay, so the line density is equal to some proportionality constant times the electric field. Okay, now another thing I'd like to just say again is looking at this, we had this analogy again that, remember we had this analogy that if you had a plane perpendicular to the flow versus a plane that was not perpendicular to the flow, was much larger, we wanted to make sure that the number of lines crossed is the same, although this area is bigger, and therefore that's why we're calling this area perpendicular. So it's a dot product of the vectors between this and the vector for the area, which we said is perpendicular to the surface. In this case, it'd be like that. Okay, so just a reminder that. Okay, so let's call this equation 1, so I can refer to it again. So this is called equation 1. So if I was gonna rewrite with a new sort of definitions, let me say that I'm going to call phi sub s number of So this is the left-hand side of equation 1. So phi sub s is number of lines. So I'm just giving it a definition. Phi sub s, lines crossing sphere S. And we're going to call this flux. And also that phi sub s is equal to the line density. Okay, this is how many lines we have per unit area times the area. And so this is, because we're talking about the left-hand side equation, this is the number of lines crossing the sphere S. So you're going to use area of sphere S. Okay. So the line density, we said, is proportional to the electric field with a constant factor. You'll see in a second why I'm not being too picky about the constant, because it tends to cancel out. But for a second, say this, we define the line density as being a constant times an electric field. So it's going to equal to constant times the electric field times the area of the sphere is 4 pi r squared. Okay, so that's the left-hand side of equation 1. Okay. Now the right-hand side of equation 1 gets a little bit more complicated. So the right-hand side of equation 1, that's this guy here. It's the number of lines crossing S prime, which is this weird shape that we drew. It's like any shape, as long as, again, it has to completely cover or encompass the charge, whatever charges are in the sphere as well. Okay, so right-hand side, we're going to call that phi sub s prime, is the number of lines crossing S prime. And again, this gets more complicated because, let me copy this shape over here so we can refer to it. Okay. This gets more complicated because of a couple of reasons. So first reason, so say complications to figuring out phi sub s prime. So the first complication is that the E field is not always perpendicular to the area vector. So I kind of drew that here. Had this E field here. And again, if I zoom in, if I think about the area vector, remember the area vector is perpendicular. So the area, we're talking about each, so let me just draw it here. So we're saying each of these, we can divide this area of this green shape into a bunch of little areas. Each one of them is called dA, so a very tiny area. And that's the dA is the actual area. And then we also need to say, like, what's the direction of the area, in the sense that what's the tilt, what's the yaw, what's the pitch of this thing. And so we basically define a vector perpendicular to this area, perpendicular to this area dA, and we call that whole thing. So dA includes both the information about this being this tiny area plus there's a vector associated with it, but the vector is perpendicular to the actual area. So if I was going to write the d sub a for this part, oops, for this little bit, its area vector would be pointing in that direction because it's perpendicular to that area. This would be that would be d sub a for that. And this would be d sub a for this. Okay, so we've divided this area of this weird shape into these d sub a's, and each d sub a has a amplitude component, which is this tiny area, and a vector component. Now, so the first problem is that in the case of the sphere, because we had a radial, so looking at a sphere, if I'd drawn it well, since we have a radial electric field, because we have a point charge at the center, the electric field is guaranteed to be radial, and we picked a sphere as the shape, this electric field is always parallel to is always perpendicular to the area of the sphere, meaning it is parallel to this d sub a, and we could just multiply it. Where was that? Yeah, we could just multiply it. We didn't have to be this area perpendicular. We didn't have to worry about it being some dot product. But here, it is going to have to be a dot product again because, like again, imagine this one. The area here would be pointing this way. So I would have to figure out the dot product between this electric field and this area. Okay, so for each point. Okay, so that's reason one, is that E sub r is not guaranteed to be perpendicular to S prime in every bit of S prime's area. So we'd have to calculate E dot dA at every location. Okay, and then the second reason why things are complicated is that the strength of E sub r will also vary across S prime. So imagine here, this distance isn't guaranteed to be the same as, I don't know, this distance, okay, on S prime. And remember, the electric field is a function of 1 over r squared. In the case of a sphere, this distance will be the same as this distance, as this distance, as this distance, as this distance along the sphere. It's guaranteed. So as you're going around trying to find the electric field around the sphere, all the strengths are the same, but it's not the case for this funky whatever. Again, I could have drawn this like that. Imagine this distance versus that distance. I'm talking about I could have drawn any shape for S prime. I guess I probably should have picked something funkier to make it more obvious. But so again, for S prime, for S, we had two big advantages. One was that the strength of the electric field was the same all along the sphere because the charge is at the center. So the distances are all the same at anywhere along the sphere. And because it's a sphere and because the electric field coming out of a point charge is radial, the direction of the electric field or force lines are always perpendicular to the area. So that's two huge advantages where we could just read off the number of the line density and the area of the sphere. That's the problem with any old random choice of shapes, again, for S prime, is that the same two things go against you here. One is that you don't know, this electric field's coming out, depending on how you drew this shape, that could be perpendicular to the shape or not, or there could be any angle compared to the shape, depending on where they're coming out. They could be coming out here, here, could be coming out any angle. So you have to calculate what part of that electric field is perpendicular to the area. Okay, and the second thing is the distance that the electric field has from the charge at any point on this weird area is going to be different. So you can't count on the strength either. Okay, so those are the two issues you have, okay, with S prime. Okay, so but what do you know, I guess? So let's figure think about what we do know. So let's take this guy again. Copy it over here. And then what should I do here? No, that's worthwhile for me to try to erase all this other stuff. So I'm just trying to keep the shape of S prime. Oops. Okay. So what is still true though is that if we pick, we can still divide this S prime into a bunch of areas. Each one of them is dA prime, and each one of these each one of these areas you're gonna have a certain lines going across. We just don't know what um, the angular position of these lines are going to be with respect to this area, and we don't know the strength. But in each one of these areas, there will be electric field lines crossing this. There'll be electric field lines if we say dA here. And again, remember the green S prime is a shape that's completely, it's like a three-dimensional shape. It's not a 2D shape. So I have to draw it as a 2D shape, but it's like as if it was a weird sphere in three-dimensional space. It's completely encompassing this charge. Okay. Anyway, just remember, keep that in mind. So anyway, here this area would have its own lines going across it. This area would have its own lines going across it. So this equation that we have, that phi sub s prime, which is defined as lines crossing S prime, we could still hold that this is an equation that you would basically do ER dot dA. Okay, so again, the times C, which is our constant. So this still holds, right? Because what we're saying is ER, the number of lines crossing, if we went through and each one of these areas, we figured out what was the component, what was the amplitude of the electric field in each one of these areas, all over the surface of this S prime, and figured out what part of those electric field values, the direction also, like how it related to the direction of the area, and we integrated over that whole closed surface times the constant, which is what's the reason for the constant again is we're saying the lines, and those lines are proportional with the proportionality constant to the electric field. This still holds, except it's just a very difficult thing to try to calculate for a funky shape. It was really easy to calculate for a sphere because dA was really easy to calculate. And we could just do that integral, and we didn't really even have to integrate. We could just sort of visually see it, right? But here, you actually have to do the integral, and it's a difficult integral to calculate. Okay, but again, going back to our equation one, from the get-go, we said that we knew that visually that the number of lines crossing S is equal to the number of lines crossing S prime. Okay, so we can go back to that equation. So number of, so number of lines crossing S, so this was the sphere, is equal to the number, this was equation one, for the number of lines crossing S prime, so that's any shape, and we call this phi sub S, and we call this phi sub S prime. And we came up with an easy expression for this, which was C E sub R 4 pi R squared. So this was this one, and we could just sort of almost read that off because it's a sphere, and we have a radial electric field coming from a point charge. So that's equal to this equation here. So C integral ER dot dA. And again, guys, this is a double integral, means you're integrating over a surface. Okay, single integral, again, wouldn't be that, but anyway, so it's integrating over surface, and the circle here means it's a closed surface because this is completely enclosing, like a surface could be like an orange peel that you peeled off, so it doesn't have to be completely closed, but this has to be a completely closed surface around this. Otherwise, you couldn't guarantee that the number of lines crossing a sphere would equal to the number of lines crossing this other shape. Okay. So anyway, so now here we are with this equation. This is a rewriting of equation one. Okay, and now we can cross the C's out. We have C's on this constant, proportionality constant, between the number of lines in electric field. And so now we see why we don't really care what this constant was as long as we kept it as a constant, because it just goes away. Okay, so now again, I'm going to remind you of the expression for electric field is electric field is let's see, is Q over 4 pi epsilon naught 1 over R squared. So Q over, I've just rewrite this thing. Q over epsilon, well, let me just put it this way. So E sub, shoot. So E sub R 4 pi R squared is Q over epsilon naught. Just rewriting this. So I can just say this is Q over epsilon naught is equal to the surface integral of a closed surface of E sub R dot dA. Okay. Okay, so this is kind of like the first starting point of Gauss's law here. Okay, so starting point of Gauss's law. Okay, so basically what we're saying, just to draw it in another way, that if you had a charge, you could surround that charge with any shaped surface. I'm going to stop calling this funky shaped surface S prime. I'm just going to call it S. So you could enclose it with any funky shaped surface, whatever you like, and that, just redrawing this, that the, the integral of the electric field times the area, again in vector form though, dot over an enclosed surface S is Q over epsilon naught, with Q being the charge you're enclosing. Okay, and the key thing is that this does not depend on the details of the surface S. Okay, so this S could be any old shape, but this equation is guaranteed to hold, that as long as you complete this shape of S completely encloses this charge Q, this relationship between the electric field times the area is going to hold. Okay, and so you should, everybody, I guess, at this point should know how to calculate this. And by that, I don't mean like knowing how to do the actual integral. Yeah, the integral is going to be, difficult to do. But what you would do, let's say you had a computer or something, you had this sort of weird shape, you could go and divide this into a bunch of little areas, D sub A, with a direction, and you'd have a direction of electric field in each one of these places, and then you could basically integrate, sum all those up in this integral and come up with this left-hand side. So I'm not talking about doing that. Everybody should know how to do these really difficult sort of enclosed surface integrals. I would, I think nobody could, but depending on the surface. But like theoretically, you should know that's what we mean basically by this left-hand side, is that you would divide the surface by these little blocks and then figure out the direction of the electric field there and the vertical direction from the surface, and you'd calculate this part, and that would be equal to the total charge enclosed divided by epsilon naught. Okay, so let's see what would happen if you had more than one charge. As you can imagine, I think you guys can guess what happens if you had more than one charge. So we had a plus Q here, and then let's say you had another charge. So this is a Q1, Q2. What would happen is, because we have this, our superposition principle, is that the electric field caused by both of them is equal to the electric field caused by each of them summed together in vector form. So in that case, we could say that in the case of, let's say if you had two charges, we could express this left-hand side of this equation as, it would be surface integral of E1 dot dA plus surface integral E2 dot dA is Q1 over epsilon naught plus Q2 over epsilon naught. Again, by superposition. Okay, and then once you have two charges, you can make this generally into many charges. So let's say you have a bunch of charges. So in a general case, so I'm going from this. This is, a any surface surrounding a charge, and I'm extending this to many charges. So two charges. So this is many charges, and so in a general case of many charges enclosed by S, I would end up with surface integral E dot dA is equal to, let's say you had, I don't know, n charges or something, Q sub I over epsilon naught. And this would be S, okay, over the surface. So another way, by the way, of saying S, which, so if, let's say if we say, we define S, let's see, define S as the boundary of a volume V, then we could also say this is, the way they write that is dV, okay, so is equal to dV. So you're basically integrating over the surface. So the boundary of a volume is the surface of that volume, okay? And a notation for that is dV. So I'm going to start writing this dV. And then here I'm going to say I is whatever charges is in V. So I, so all V is the volume. So V is volume, and we're talking about all the charges in this volume. Okay, and this basically, so this is kind of starting to get to the almost to the final stage of Gauss's law. So we're talking about the summation of all the charges is equal to this area vector dot vector, and so, and this goes with like any shape, right? So this holds for any shape. So let's say I draw a truly funky shape. So I'm going to put a Q charge here, and I'm going to try to draw a shape, a little heart shape here. How's that? And then, like, will it hold across? This is the surface. And the answer is yes. So now if you think about the electric field lines coming out of this in this direction, whatever, I'm just going to draw the electric field lines. Notice I'm being a little sloppy here. It should be symmetric around this, but my point was here is if you have multiple in and out, these guys sort of don't mean anything because they'll sort of cancel each other out. So all you're really, you have, this is one line going out, one line coming in. Okay, so this doesn't matter. That numbering the counting will cancel each other out. So really end up with this guy leaving this one count for this line force. So even if you have a shape where you have multiple exits and entrances of electric field lines, as long as those are, it doesn't matter, right? You just basically subtract one from the other and you end up with the one exit. Okay, so it holds, this equation will hold true for any shape as long as it's completely enclosing the charge. Okay, So now we're ready to talk about the final form of the of Gauss's law. Is that suppose Q is a continuous, what really murdered continuous I don't know, clump of charge. Okay, so again, and let's draw it in a XYZ space. So let's say that we had a little volume in XYZ space that was X, Y, Z, that was dx, dy, dz on a side, and rho, the charge density, dx, dy, dz, is the charge in the cube, which is this guy. Okay, so we'd have the charges would be charge density times the volume would dilute the charge in this little cube. And so if we talk about charge density, we'd end up with, we're basically replacing this summation with a charge density in the case where you have a continuum of charges. Now we know that charges are discrete. They come in units of 1.6 times 10 to the minus 19, they're either electrons or protons. But if you move if you imagine you're far from billions of charge units all kind of packed together, you can kind of think about it as a continuous charge density. Okay, so it makes it easier to talk about doing integrals than do summations. Okay, so that's the idea behind that. So again, the surface, this E dot dA is equal to 1 over epsilon naught times this volume integral of rho x, y, z, dx, dy, dz. Okay, and this is, so in words, this is basically all the charges inside V. Okay, and then this is the final form of Gauss's law. Okay, voice is about going. Hopefully that was helpful for you guys as a review of Gauss's law. Anyway, hopefully it made a little bit more sense. Anyway, hopefully I'll see you guys this Friday. Thanks. Bye.